Oh, there we go.
Yeah, we're live.
Greetings, fellow nerds. Welcome to another episode of Between Two Nerds, where we talk with prominent guests about all aspects of the networking industry, from protocols old and new to industry trends and drivers to up and coming technologies, and as always, things you should know to further your career. Well, today we don't really have a guest, prominent or otherwise. Jeff and I are just getting back to the roots of this show, and it was just the two of us talking technology, and we're going to do that today. Hi, Jeff.
Hi, Jeff. Great to see you.
Good to see you too. Um, uh, so we're going to talk. This is sort of a prerequisite, I guess, of a show that we wanted to do on BGP over QUIC. And our last show, Mark Blanchet sort of did sorry for the pun, a quick overview of QUIC. And we just thought it would be a good idea to do a little bit more in depth to set the stage for BGP over QUIC. Does that make sense, Jeff?
Oh, absolutely. Jeff, do you see anything different about me?
Let me see here.
Sorry, it was a rhetorical question. I'm a grandfather, been for 2 days.
Oh, really? Oh, here I am looking at your face thinking, oh, what, new glasses or what? Congratulations.
Thank you.
Boy or girl?
Boy.
A boy. Oh,
Big one.
yeah. Those are awesome. I got to tell you, granddaughters are pretty cool too. But congratulations.
Thank you. I'm really excited. The first one.
Yeah. I got 5 of the little critters now.
So you got used to it.
Yeah, maybe not for long. So anyway, yeah, that is cool. Hey, listen, before we even get started on the topic of the day, I want to do a book plug. My friend Aninda Chatterjee has this new book out, Juniper Data Centers with EVPN VXLAN. And Jeff, I know you and I have maybe talked once or twice about this topic on the show. Beyond just it being a Juniper book, sorry for my dog in the background. He always knows when I'm in meetings. It's just a really in-depth coverage of the technology. And maybe I'm a little bit prejudiced because I was a tech reviewer on the book, but I think it's the best book on the market right now on just the technology, and then looking at how to implement the technology on Juniper. So anyway, that's my plug for the day. But we're here to talk about QUIC, and I am going to share
You
my.
better be quick.
What's that?
You better be quick.
I better be quick. Hopefully everybody can see my slides. Do you see them, Jeff?
No, not yet.
Not yet. Robert, can you see the slides? That's weird. We tested it right before. On this show, for all the many guests that we've had sharing slides, I've never shared slides myself. And,
you need to share them again.
Okay, hang on a second. Let me. I knew I would end up fumbling through this. Oh, you know what I forgot? I forgot to actually do the share screen part. Let's see here. Entire screen. Share. Speaking of grandkids. Okay, do you see it now?
It's coming up. Yes.
Okay, great. Yeah. So, like I said, I haven't actually done slide sharing before for this show, so being a little inept here. So Jeff, I'm just going to kind of start jabbering through these slides. By all means, jump in at any point. So, first of all, what is QUIC? It's sort of. I think I've already done one pun on this show. And it sort of gives some it sort of opens itself to puns, but QUIC was originally developed by Google, and originally it was an acronym for Quick UDP Internet Connections. Since it has been adopted by the IETF, it's really just a name now. They're not using the acronym anymore. In fact, I think at one point when it started, I think it was even called GQuick, if I remember. But it's a general purpose connection oriented protocol, and has TLS integrated to it for encryption. And little question on that last bullet there is, will QUIC replace TCP? And I've got a slide right towards the end of that kind of addresses that. But it's actually intended as a replacement for TCP. And why? It probably calls for first a networking 101 review of TCP. We've got
Jeff, I would like to emphasize your point of IETF. So this is how the industry should develop their protocols, right? Originally, completely Google inside proposals were brought to IETF. We formed the working group that resulted in beautifully written RFC 8200s and a whole bunch of different work. And IETF QUIC looks quite different than original Google proposal. It works much better. It's much better acceptable by operators. So this is what kind of bringing your work to community allows you to do. So be a good citizen, be like Google in this case. Bring your work to community, let us develop it, let's make sure it interops, make sure that all the stakeholders, and there are many of them on internet, actually can deal with it. That's an amazing example of how very, very large companies that could have pushed it through our throats because they're who they are, brought it to the community, iterated over many years, was kind of, was willing to invest in terms of people, time, to build something that is developed by community, accepted by community. And again, it's an amazing example of how industry should be dealing with new things.
That's perfect. Thank you. That's an excellent point. So yeah, like I said, I think everybody knows TCP. Anybody watching this show anyway, you learned TCP a long time ago. So it's basically IP is a connectionless protocol. TCP just gives the a connection-oriented service, the appearance of a point-to-point connection over this connectionless IP, through a three-way handshake for assured connection, sequencing retransmits, by acknowledging the receipt of segments, and depending on the version of TCP, there's a lot of versions of TCP out there, by the way. Some offer some flow control, some forward error correction, things like that. But the price you pay for all of those things with TCP is that it can be slow. And UDP, which was actually developed sort of at the same time as TCP, maybe a little bit after TCP, with the idea of, well, not everybody needs a connection-oriented service. And it was acknowledged even back then that UDP would be much faster for applications that didn't need that connection-oriented mechanism. It's primarily, you'll find time-critical apps like DNS, a lot of video and music streaming, gaming, and things like that, which use UDP because it's faster. And to understand maybe the problem with TCP, and this really goes back to the history of HTTP, and it probably doesn't take much to understand why Google at this point is getting involved and is concerned about this. But the original version of HTTP 1.0, clients established a TCP session every time they fetched, oh, there's a little typo in there. They fetched data from the server, which was an obvious waste of resources. So along came HTTP 1.1, which supported reusing an existing TCP session. And that was implemented with, TTP, HTTP header keep alive. But it was susceptible to head of line blocking, and we'll talk a little bit specifically about multiplexing and head of line blocking as we get further on. But everybody kind of understands HOL. That you get a series of small files, a larger file in front of it. At least that's the idea of head of line blocking in buffers. That all these small files have to wait for a larger file. With TCP, it's you might have a series of packets already buffered up and ready to go, but you've lost a packet in the TCP sequence, and all these other packets have to wait for that one packet to be retransmitted. And that is where HOL blocking comes in with HTTP. So with HTTP 2.0, it solved somewhat the header line blocking problem with multiplexing, but you still have to wait for retransmissions during packet losses and things like that. So the question became, well, do we enhance TCP or replace it? And that sort of gives you a recollection of OSI modularity and the whole idea that you learned, again, networking 101, that with modularity, you could just plug something new into that transmission layer in this particular case. And so is that a good thing to do? Well, part of the challenge is that code for TCP exists in kernel space and not in the user space. So that's sort of, given that problem statement very briefly, that's where QUIC comes in, and already mentioned it was developed by Google. Google has some very obvious interests in optimizing HTTP. With the IETF now, Jeff, as you just mentioned, it's standardized in RFC 9000. There is a QUIC version 2, which is the current version, and that's RFC 9369. You'll find that RFC is fairly short. It has some modifications over QUIC version 1, but in reality, if you want to really learn QUIC in depth, you should read RFC 9000 because that's the real details behind it. And that's what I kind of followed, throwing together these slides. One of the advantages of QUIC is that it resides in a user space, not the kernel space, and it exists as a wrapper on top of UDP, not as a new transmission layer protocol. So it takes some of the best features of TCP, like packet retransmission, multiplexing, congestion control, and adds them to UDP. And we have a new version of HTTP, which is HTTP 3. I have a really hard time saying that acronym, which runs on top of QUIC. I've got a illustration here that I actually...
Just a second, I wanted to say a couple of points here. So, number one, I think I said 9200, it's actually 9000. So somehow I got mixed. What's important here, and you might not realize it, but some of applications in your phone implement full TCP/IP stack within application space, right? So usually it works kind of weird when you have applications spitting out UDP that goes over TCP. Mm-hmm. So QUIC fundamentally is solving this problem by proper layering of what's in kernel, what's in user space. So you don't really need to, do it on application layer. It's wrong. And another probably important point, outside of HTTP 1.0, which was really naive, where you kind of follow server-client model, every time you need to fetch your open TCP session, all problems Jeff described are really user experience problem. But at the end, you just wait longer for screen of beautiful pictures to show up. So it's very, very user-focused feature. Its main goal is to make you as someone who's using HTTP to get content faster, to get it right way without any transport issues.
Absolutely. Yeah, so I threw this this drawing together. I sort of stole elements of this drawing from a couple of different sources, primarily from Google itself, but F5 has a presentation on QUIC that had some nice elements to it that I wanted to add. So so I tried to credit both down here, but you see almost any overview of QUIC, you'll see a drawing very similar to this. So on the left-hand side, you can see working up through the TCP/IP layer, maybe more than the OSI layer. At the network layer, obviously we still have IP. Traditionally, above it, we have TCP, which does packetization, reliability, congestion control, and all of that. If you want security, security is not really a separate layer, but nevertheless, typically it's TLS 1.2, which takes care of encryption and decryption, key negotiation, authentication, those sorts of things you would expect to see. And then the application is HTTP 2 here for request response, and this is a key piece, stream multiplexing. So going to QUIC, obviously, UDP, just like TCP, takes care of packetization, and QUIC resides on top of that. And you can see that where TCP had reliability and congestion control, QUIC adds that on top of UDP. So same pieces there. And by the way, sort of how all these things line up, between QUIC and TCP and TLS and so forth, that's sort of important how that works too. QUIC takes care of encryption and decryption, which would be, TLS 1.2 here. It's integrated with QUIC. And the really key point is, QUIC takes care of stream multiplexing where, it was at the application layer for HTTP 2. So now we've got HTTP 3. Got to learn to say that before the end of this show. We now have the requests and response and same as HTTP 2. And TLS 1.3, which is part of QUIC, takes care of authentication and key negotiation. Some of these illustrations, you'll actually see TLS 1.3 integrated down here in the drawing into QUIC itself. I personally, in my own mind, it fits better sitting on top of QUIC rather than sort of being integrated into it, even though it is integrated. Jeff, you had something there?
No, I'm just nodding in agreement.
Oh, okay.
It makes much more sense to show it the way you do.
I'm sorry?
It makes much more sense to show it the way you do.
Yeah. Oh, thanks. I appreciate the validation, because I was just thinking, well, makes sense to me. So some characteristics of QUIC. There is no three-way handshake, and I've got a slide on that. It has a much faster handshake, which addresses a lot of the initial latency of TCP. And I've already said it adds reliability on top of UDP. You've seen that. Another piece that's kind of key here is that the stream is identified by a stream ID, and multiple streams can be sent over a single channel. There's some interesting conceptual pieces of that. I'll talk about that. We'll talk about two types of stream. Connections are not bound to a single network path, which is really important because this means that if the network path changes or address mappings change, QUIC sessions will not break the way TCP sessions will break. I'll talk about that a bit more. Um, and uses multiplexing. We'll talk about a little bit more about that. And security, sort of already mentioned. I'm not going to go much into security, but it does use TLS 1.3. So some advantages. Again, I may have already sort of visited all this, but if you look at a comparable TCP session with TLS with HTTP2, connection latency is reduced. There's improved multiplexing without header line blocking. There is connection migration, improved congestion control, improved congestion avoidance via bandwidth estimation, forward error correction, and as far as support goes, it's interesting. In putting together these slides, I was doing a lot of exploring around on what do people think about QUIC and all of that, and if you look at somebody like Google or Facebook, they'll say, oh yeah, there's wide adoption of QUIC. Google is obviously using QUIC very widely. Facebook, even a couple of years ago, said some 73% now of their sessions run over QUIC. Firefox, looking at some specific users like Uber, Microsoft, Akamai are using QUIC. So there's quite a bit of adoption for it. So that's an important point to make. This is the terminology can be a little bit weird with QUIC, not weird, but confusing. And I found this illustration under a blog by Oliver Leroy, and I stole it. This is sort of my own drawing, but he has a much prettier drawing. But just as an example here, and before I get to that, that a quick connection can probably be equated to a TCP session opened between two peers, but then things get weird. So a quick connection contains one or more QUIC packets. Each packet contains one or more frames, and that's where the confusion comes in, because people start thinking in terms of OSI and TCP, layers, where packets are really, the network layer, frames are the data link layer. And all of this is happening at the transport layer in QUIC. So we have packets and frames at that layer. And each frame represents a stream. Sorry, I went ahead too much there. So, here's an example of a quick connection. And that connection has a connection ID between a client and server. Inside that, you can see, there are a number of QUIC packets and a continuation there. And inside those packets are stream representations. So here we've got, and those streams are represented as frames. So here's stream 1, stream 2. In this packet, we've got 3 QUIC frames. There's a continuation of stream 1. And then we have stream 3, stream 4. And here we have stream 2 again inside this third packet. So hopefully that sort of at least gets you oriented to the terminology that's used with QUIC, which is pretty easy to grasp once you get the idea that when you're talking about packets and frames in QUIC, it's not quite the same context as the overall OSI model that we're all used to. And the other concept here is, getting two streams, how you identify them. First of all, streams can be bidirectional or unidirectional, and that's identified by a 62-bit stream ID. It's really 64 bits, but the last 2 bits are significant. The least significant bit identifies whether the stream is server initiated or client initiated. If they're odd numbered stream IDs, it's server initiated. If there are even numbered stream IDs, it's client initiated. And then the second least significant bit uh, uh, describes also whether it's bidirectional or unidirectional. So, we uh, begin when you number streams, it begins at a minimum value, and each additional stream is incremented by one. So you increase the numbers beginning from a minimum value. Um, Multiplexing, and Jeff, I know you had mentioned, hey, we need to be sure to emphasize this because this is important for BGP over QUIC. HTTP2, the application sees the TCP connection as a stream of bytes. We were talking about header-line blocking. When a packet is lost, no other packets continue until that lost packet is retransmitted. Everybody knows this about TCP, that the receiver, acknowledges received packets and or received segments, really, in TCP language. And when one is lost, you wait till that is retransmitted, then everything else can continue, and that's where the header line blocking comes in with HTTP2. With QUIC, it's designed specifically for multiplex operation. In fact, if you look at RFC 9000, you'll see that multiplex is right there in the title for the specification. So lost packets are associated with a stream, and if something is lost, it only affects that one stream. Other streams can continue uninhibited. And again, stole another nice illustration, this one from Auvik. I like this one, so instead of building my own, I just was lazy and used theirs. But if you look at HTTP2, a client sends a request to a server for data. The server is sending this stream back. You can see it sequentially in this TCP connection. And let's say segment number 2 is lost. Everything else, 3 through 8, might be buffered up somewhere in the internet and is ready to be forwarded, but everything has to wait until the client can signal to the server, hey, I did not receive segment 2, and the server has to retransmit that. With QUIC, the server, you get the same request, client to server, and the server sends multiple streams. And here you can see, I've got segment 1, 2, 3, 4, 5, 6, 7, and 8 on separate streams here. And here, if segment 2 is lost, the only thing that's really going to get blocked on this stream is segment 3. Everything else can continue. They're on separate streams, and everything works fine. Jeff, do you have anything you want to add to this part?
Yeah. So there's a question on chat: why firewall vendors hate QUIC?
I've actually got I've got a mention on that at the conclusion, and the reason is because QUIC is running over stream IDs. Plus, there's integrated encryption and that sort of thing, and it becomes much more difficult for individual streams to be correctly identified and analyzed. It's not only firewalls, but it's also a challenge for troubleshooting.
Yeah.
Because it's not just a matter of I'm just going to look at this source and destination address and port and be able to identify a stream.
I think the kind of intention of QUIC since day one was the less we expose, the more secure is the user. Right? Kind of fundamental approach to QUIC, which resulted in most of the QUIC header being encrypted. Right? So the less you can see, the less you can derive what the traffic is, And obviously, if you're an enterprise, you would like to be able to analyze every bit of traffic that's coming to your network.
Yeah.
So QUIC wouldn't allow that. TLS 1.3, from security perspective, has been really, really hot topic for years. How
Yeah.
do you actually deal with it? How do you distribute certificates? And all of this kind of, I mean, TLS 1.3 was kind of problematic from an enterprise perspective. QUIC natively integrates 1.3, right? So that was a problem. Another one, there's actually draft in ATF that talks about how to tunnel stuff over QUIC. So theoretically, you can establish channel out of your enterprise over somewhere else over QUIC, and no firewall can see it, right?
Yeah.
Unless you do some heuristical analysis. So all of this made people who want to know exactly what's going in, what's going out, really to hate it. And it's understandable, but it's inevitable. I think after revelation of what's going on with security in AT a couple of years ago, due to some people moving to some other countries, the movement of encrypt everything has been very, very strong. So QUIC is completely in line with it, and it's a trade-off of development of technology.
Yeah. And it's my understanding that there are the firewalls are starting to adapt. That some will have adapted at least somewhat to QUIC.
Yeah.
And same thing for troubleshooting. The latest version of Wireshark will allow you to look at QUIC.
And while we kind of present it as a new protocol, there's huge amount of QUIC traffic on the internet. Right?
Yeah.
In some countries, it's over 50%. So half of it is probably YouTube. So YouTube is completely over QUIC. Half of it is different sources. The QUIC has interesting behavior, right? If you cannot establish QUIC session, the server might say, let's go back to HTTP2.
Yeah.
Which is kind of very nasty behavior.
Mm-hmm.
So there's another question from Madan. Would BGP over QUIC BBA TCP OA? It would, because TCP OA is built in, it's not really BGP type of feature. It's built on top of TCP. So BGP over QUIC would natively use TLS. It's not something we cover widely in the draft, so which is going to be kind of one of the next talks here. But the security part is going to be completely taken by the TLS.
All right. Thank you for that. I'm going to go kind of quickly through some of these other slides. Jeff, I know you've got kind of a hard stop today, but I think we're actually already hitting most of the important points. But just a few bits, and this is maybe getting a little bit more down into the weeds. For stream states. QUIC has two stream state machines, one for a transmitting endpoint and one for a receiving endpoint. And as I think I mentioned earlier, QUIC can have either unidirectional or bidirectional streams. And if it's bidirectional, then you're going to be using both state machines. I'm not going to go into all of the states here. If we really want to maybe more of a deep dive on QUIC, we can talk more about that in a future session. But nevertheless, here's the state machines for both a sender and a receiver, with the data acknowledgments and all of that. For flow control. Let's see. There's a few other pieces I kind of want to get to, so I think I'm going to skip past the most of this section here. But as far as acts go, with QUIC you can carry explicit information about delay between receipt of a packet and an act being sent, and can carry up to 256 NAC values. Which reduces reordering problems. And for connections, this is the part I really wanted to get to. that I think is important. The quick handshake to appear requires, at least for the initial setup, one round trip versus TCP. Ooh, there's another typo that requires 2 to 4 round trips, and subsequent handshakes with QUIC, making it quick, is requires no round trips. And each connection carries one or more 64-bit connection IDs. I talked about that a little bit earlier. And version is negotiated at connection. You can have a cryptographic handshake using TLS. And here's what I wanted to show as an example with TCP. And by the way, this, again, stealing this illustration from Google, a TCP handshake is going to take, a round trip, say, of 100 milliseconds with, a minimum of 2 round trips. And if TCP, comparing it more to QUIC, is using also TLS, you've got, 4 round trips, which means for the initial connection, it's going to be 200 milliseconds. And for subsequent connections, sorry, I'm getting that backwards. For any connection, if it's a repeat, but if the connection has never been connected before, the round trip can be up to 300 milliseconds. Whereas QUIC, you can see here for an initial connection, it's literally one round trip. So 100 milliseconds comparing to TCP, but subsequent connections is 0 milliseconds because you don't need a second round trip handshake. For address and path validation, this is a really key part too. Address validation assures that the endpoint can't be used for any kind of traffic amplification attack and prevents source address spoofing. Path validation means that you can still have reachability after an address change. When you have a TCP connection, everybody knows this part. It's TCP is identified by a 4-tuple of the address, source address and source port, and the destination address, destination port. This kind of goes into what we were talking about with why firewalls kind of hate QUIC, because this is an identification everybody knows how to use. But the problem is that if you have a change in your connection, like you are moving from your Wi-Fi network to a cellular network, or you have a NAT rebinding that causes a port change on the port association, those will break TCP sessions. Whereas a QUIC connection, because it's identified by a connection ID rather than this 4-tuple, the address change doesn't affect the connection, and a path change doesn't affect the connection, and that's a key point for QUIC. Forward error control. I'm going to just kind of go right past that, but it is a capability in QUIC. Last slide here, Jeff. I'm actually thinking I'm going to be able to get you out at 40 minutes after the hour, like you asked. I did some looking around. I know there's some comments from Bruce Davey out there, that QUIC solves a different problem than TCP. That may be true, and not everything needs encryption. So out of that, the answer may be, well, QUIC probably won't replace TCP. And Jeff, I'm just guessing you're going to have some strong opinions here.
Yeah. So for foreseeable future, all of the changes are usually business driven, right?
Mm-hmm.
But in this case, as long as we can make both protocols coexist peacefully, and it's not just QUIC versus TCP, right? It's TCP cubic versus TCP other congestion, because we've seen really, really bad behaviors. That's why, again, most of this development is done by Google and people of this kind of companies. And all of this traffic goes over internet eventually, right? So if you have new type of TCP congestion pushing out old one, and you just said TCP is in the kernel, right? And I mean, the variety of different implementations and OS's different behaviors is going to exist forever, pretty much. So if you have one protocol that's eating another protocol, that's a huge problem, right? So practically, one of the main things that ITF does is to make sure that when we put all the stuff on internet, they actually peacefully coexist. And this is kind of back to Jeff's question. QUIC is superior to like HTTP 2.1 is in many ways. There's also DNS over QUIC, right? The DOH and all the developments are going on. QUIC is supported by pretty much any large company from Meta to Google to Akamai. Any large CDN supports QUIC today. So it's there. In some countries, it's over 50% of total traffic. Practically, I would expect both to coexist for a really, really long time. There's a question from Mazen on QUIC streams of BGP IFSF encodings. That's actually what we are doing. I would really advise you to read the draft.
Yeah.
This is main motivation to decouple fate of different IFSFs from the fate of BGP session itself, right? So today, in all BGP implementations, there are coupled. So if your EVPN signaling causes notification, your IPv4 unicast will go down as well. So this is problem kind of that we are trying to solve in QUIC. Again, we will talk about the ITF work much more extensively here with additional people. Practically, so multi-stream capabilities of QUIC are one of the most interesting features for BGP.
Absolutely. And with that, Jeff, I know you need to get out of here, but that was a nice plug for our next show, which will be BGP over QUIC. So, Jeff, thanks.
Thanks, everyone. Thanks, Jeff. Thanks specifically to keeping it under time. Really appreciate it.
Oh, yeah. I talked really fast through that. So anyway, we're going to be out. Jeff, have a good next meeting, and I'll see you in a couple of weeks.
See you, Jeff. Everyone, thanks. Bye.